So introduction about electrical machines. So in that electrical machines, we are taking that will be generators and motors. So these two are comes under the category of electrical machines. So generator or motor, that electrical machines is nothing but conversion of energy from one form to another form. One form to another form. So in the type of generator, so the mechanical energy is converted into electrical energy. In order to provide the mechanical energy, we have to take that prime mover. The prime mover which gives that mechanical energy and it produces that electrical energy. So in that input, mechanical input is given and we have to get that output will be electrical. output. Similarly, the motor. So generator is the machine which converts that mechanical energy into electrical energy. For providing the mechanical energy, we have to take a prime mover, which gives the mechanical input, and it converts the mechanical input energy into electrical output. So motor is also the machine which converts electrical energy into mechanical energy. Mechanical energy. So in the case of electrical energy, so we are giving that electrical input, and which produces the mechanical output. So in the mechanical output, we can get in terms of torque. So there is a twisting moment which will occur at the center of axis. So with the help of that, we can calculate the mechanical output. That is P is equal to output power 2 pi mt by 3. So in the electrical input will be, we can take in terms of voltage and current. So here we are giving that will be both machines which converts electrical into mechanical is motor, mechanical to electrical will be the generator. In the types of generator and the working principle of generator and motor both will be based on the Faraday's laws of electromagnetic induction. Whenever conductor cuts the flux, EMF is induced. So induced EMF is directly proportional to rate of change of flux linkage. So in the case of generator, the production of EMF, that is dynamically induced EMF, production of dynamically induced EMF, production of dynamically induced EMF is existed. So here we are taking the conductor which is rotated in the magnetic field, so it cuts the lines of flux. So EMF is induced. The induced EMF is directly proportional to the rate of change of flux linkage. Here we can consider the simple loop generator or single turn conductor we can consider. So in the case of the conductor which rotates in the magnetic field, so it wherever it cuts the conductor, cuts the flux, EMF is induced. So based on the position of the conductor, the induced EMF will be minimum or maximum, 0 or maximum based on the conductor position. So that induced EMF direction is determined by the Fleming's right hand rule. So the Fleming's right hand rule, so however we know, so we have to take the forefinger and thumb and middle finger which is perpendicular to each other, so that forefinger represents the direction of magnetic field. So that will be the middle finger we have to take, that will be the direction of induced EMF we can identify it. So in the case of motor, whenever the current carrying conductor, the principle will be whenever the current carrying conductor will be placed in the magnetic field, the force will be experienced based on the upward force or the downward force which is greater. Accordingly, the conductor starts to rotate in the magnetic field and cuts the flux, and EMF is induced. That induced EMF is opposes the supply voltage which is the given as the input. So that EMF is called back EMF. So that induced EMF, then the direction of current will be determined by the Fleming's left hand rule. Okay, so in the case of types of generator and types of motor, we can take in the types of generator, we can consider that will be separately excited generator and self-excited generator. In the case of motor also, we can take that will be self-excited motor. So here the types of generator, separately excited and self-excited. Separately excited, we have to excite the field windings separately. Excite the field windings. Separately. Self-excited field windings are excited within itself. Okay, so due to residual magnetism. So in the case of self-excited, again the types will be shunt excited generator, series excited generator, compound excited generator. Shunt excited means the field windings are excited and within itself, and also that is parallel to the armature winding. Series excited means series winding and armature windings are in series. In compound winding, that the field windings which are connected in parallel with both the armature winding and series field winding. Shunt winding will be, you have to take parallel with the armature. Okay. So series windings are in series with that armature winding. And the compound winding, it has both the shunt winding as well as the combination of series and armature. Shunt winding is connected in parallel with both armature and series winding. Okay. Similarly, the types of motor also we can take that will be self-excited and the shunt motor, series motor, and compound motor. In the case of generator, we are getting that the electrical energy is the output, but in the case of motor, we can give the electrical input to the motor. Okay, so in the case of types of motor, again we have to take shunt motor, series motor, and compound motor. Shunt winding or in parallel with that armature winding. In this case, we have to give the electrical power as the input. The electrical energy is given as the input. Series winding, both the series field winding and armature winding are in series. So in that case, we have to take electrical input. Compound motor, both the field winding and series winding and armature. Okay. So in the shunt field winding or in parallel series and armature winding. So again, that compound winding, compound motor is connected. They are taken into two, long shunt, short shunt. In that long shunt and short shunt again we can take into two, differentially compound, cumulatively compound. Differentially, cumulatively. Okay. So and also we have to take the characteristics of generator and characteristics of the motor. So in the characteristics of the motor, we have to take the LB. That is performance characteristics. That is we have to take in terms of speed, input current, and efficiency like that. In case of generator, we have to take that will be open circuit characteristics and load characteristics. That is internal characteristics and external characteristics. So internal characteristics we have to take that will be open circuit, that is OC characteristics, and external characteristics we have to take the respect to armature current and field current. So in the case of that is electrical machines, we have to take that will be transformer. So the transformer is also a device, that is also a static device which transfers energy, electrical energy from one circuit to another circuit. The static device transfers electrical energy from one circuit to another circuit. Okay. So in the case of transformer, we had seen already in the two classes. What are the things we have seen? The basic principle of operation of the transformer, basic principle of operation. Then The transformer EMF equation, transformer EMF equation, and transformer under no load condition and transformer under loaded condition. So in the transformer under no load condition, we can get the no load current that has been taken into two components IW and I mu. IW is nothing but I naught cos phi naught. I mu is nothing but I naught sin phi naught. So that we can calculate I naught is equal to square root of IW square plus I mu square. Okay. So in that loaded condition, we can consider that magnetic leakage also. That is magnetic leakage. Due to that, we can get that reactance X. So we can consider the winding. We have to take resistance and reactance in primary as well as secondary and the secondary. So in the primary, we can take R1 and reactance X1, secondary R2 and X2. So we have to take that will be the total impedance we can consider. With the help of that, we can transfer that secondary resistance and reactance to primary side. So secondary resistance R2 will be moved into primary side. So that is R2 dash. So R2 dash is combined with that R1. So we can identify that effective resistance in the primary R01. Similarly, X2 will be transferred into primary X2 dash. So we can take the total reactance X1 plus X2 dash equal to reactance equivalent reactance referred to primary. Effective or equivalent resistance reactance referred to primary. So R01 will be equal to R1 plus R2 dash, X01 equal to X1 plus X2 dash. Similarly, we have to transfer from primary to secondary also. So that is primary is R1 that to be transferred to secondary R1 dash already with that R2. So R2 plus R1 dash we can take R02. So that is equivalent or effective resistance referred to secondary. Similarly, X1 to be transferred to secondary. So X1 dash already with that X2 equal to X02 effective reactance referred to secondary. So R2 dash is nothing but the transfer of secondary resistance R2 to primary. That is nothing but whenever transferring resistance from secondary to primary divided by K square R2 by K square. Similarly, X2 dash equal to transfer of reactance to primary, that is equal to X2 by K square. Transfer from secondary to primary divided by K square. Then primary to secondary R1 to be transferred into secondary, that is R1 dash, that is equal to K square into R1. X1 will be transferred to secondary X1 dash equal to K square into X1. When primary to secondary transfer, we have to multiply by K square. Similarly, Z will be from the primary side that to be transferred to the or secondary side impedance will be Z02 will be transferred to primary side. So we can how we can transfer from secondary to primary means by K square. So Z02 by K square that is equivalent to Z01. That is we are transferred secondary to primary. Similarly, we can transfer primary to secondary Z01 will be primary to secondary means Z02 that is equal to K square into Z01. Okay, with the help of that we are seeing that there will be equivalent circuit also and we are taken that will be phasor diagram under no load condition, no load phasor diagram and loaded phasor diagram. So no load phasor diagram, how we can consider the no load phasor diagram with respect to no load current I naught. So I is the reference, V1 will be the voltage which is leading one, I naught is the current. We have to take I2 dash. So in that we have to identify that will be I2, it is lagging. So we have to take in that. Extend I2 to primary side I2 dash. So draw the parallelogram. We can take that will be resistance will be I1. So that is inductive load. So E2, I2 lags by an angle phi 2. If it is resistive load, or we can take I as a reference. V1 will be the voltage perpendicular and V2 will be the induced EMF over V2. We can take the voltage. So I2 will be in phase with each other. V2. So I2 dash you have to extend into primary side and you have to draw I0 will be the current, no load current. Draw the parallelogram and identify the resultant, this I1. Similarly, we can draw the loaded phasor diagram. So loaded phasor diagram. This is a loaded phasor diagram. For that, we have to take primary as well as secondary side. Primary will be in the upward direction, secondary will be in the downward direction. We have to take I will be as a reference. First, we have to draw the secondary side. E2 and I2 will be in phase with the E2. So we have to draw E1, it will be in the primary side. And I2 R2. So we are getting the primary side. E1 will be the supply voltage and drop in the resistance will be I1 R1 and drop in that reactance will be J into X1 equal to E1. Supply voltage minus drop is equal to induced EMF in the primary. Similarly, in the secondary side, EMF is induced first and drop will occur I2 into R2 plus JX2 equal to V2 or there is V2 that is V2 equal to V2 plus I2 into R2 plus J into X2. So in the case of resistive load, I2 is in phase with the V2. So I2 R2 will be in the same direction. I2 R2. So we can take that will be perpendicular to that I2 R2. We can get I2 X2 and with respect to I2 only we can consider first. So I2 R2. So E2 equal to the V2 plus I2 R2. So you can take that will be or E2 minus I2 R2. E2 is equal to minus I2 R2 which becomes V2. Similarly, I2 you have to extend the side I2 dash, I0 you have to draw and in the same direction of what is E1. E1 equal to V1 minus or V1 equal to E1 plus I1 R1. So I1 will be first you have to draw I1 this parallelogram. So in the direction of I1 you have to draw E1 I1 R1. Okay. So that will becomes E1 plus I1 R1 with respect to resistance only I have taken that is V1. Similarly, with respect to resistance. If it is inductive load, take I as the reference. It is the induced EMF in the secondary, and I2 lags by an angle phi2. In the direction of I2, we have to draw I2 R2 E2 minus I2 R2, which gives us E2. So E2 minus I2 R2. So you have to draw a take that will be E2 is the magnitude. From the direction of I2, you have to draw I2 R2 that will be opposite direction of I2. These two are in same direction, that is opposite E2 minus I2 R2, which gives V2. Okay, similarly, you have to draw in the primary side E1 and I2 we have to extend into primary side I2 dash I0, draw the parallelogram is I1. So E1 V1 minus I1 R1 equal to E1 plus I1 R1. So I1 R1 which gives E1 in the direction of I1. So I1 R1. Similarly, for leading, phasor diagram will be I will be as the reference, E2 will be induced EMF, I2 will be leading one an angle phi2. So E2 minus I2 R2 gives E2. E2 minus, so minus means you have to draw in the same direction. This is I2 R2. So E2 minus I2 R2 which gives E2. Similarly E1. So draw I2 opposite direction I2 dash. I0 is the load current. To draw the parallelogram. In order to know I1 only, we know all these things. I1 from E1, draw parallel to I1, I1 R1 and E1 plus I1 R1 which gives E1. Based on that, we have seen that will be including the reactants. There is a diagram including the reactants. Now we have to take including the R1, X1 drop also we have to consider. If in the case of resistive load, or we can take that is I is the reference, including resistance and reactance R1 X1 and R2 X2. So V1 minus I1 R1 plus JX1 equal to V1. V2 minus I2 R2 plus JX2 equal to V2. Or the rest V2 equal to, or we can write V2 plus I2 into R2 plus JX2. Because you have to take I as the reference. Secondary side E2 will be the induced EMF. E2 and I2 will be lags by an angle phi 2. So if it is resistive load, E2, I2 and V2 are in phase with each other. In the direction of I2, you have to draw I2 R2. So perpendicular to I2 R2, we should draw I2 X2, I2 X2. So the joining this I2R2 plus I2X2, which gives I2 Z2. So E2 minus I2 Z2, which gives that V2. Now taking that magnitude to differentiate. So I2 and V2 are in phase with each other in the direction of I2R2 perpendicular to that I2R2, I2X2, perpendicular means this direction. You have to extend E2. So in the case, the I2R2 plus I2X2, which gives that will be I2 Z2, E2 minus I2 Z2 gives V2. Similarly, draw that I2 dash in the opposite direction. I0 will be the loop current. Draw the parallelogram, that is I1. I1. Okay, now draw E1, E1. The direction of D1 we have to identify E1 plus I1 R1. The direction of I1 you have to draw I1 R1 perpendicular to the top that I1 X1. Joining I1 R1, I1 X1, I1 Z1. E1 plus I1 Z1 which gives E1. Similarly, if this is for resistive load. If it is, we have inductive load. So if it is inductive load, how we can draw I as the reference, E2 will be the induced EMF, I2 with respect to E2 lags by an angle phi 2. So I2 lags for V2 also. Okay, I2 lags by V2 also. So if in the case, you have to take the direction of my E2 minus I2 R2 and minus I2 Xj into Z X2 equal to V2. So the direction of I2, V2 minus, so opposite direction. So otherwise, the direction of from V2, you have to draw I2 R2, I2 R2 perpendicular to the top I2 Z2. So joining this, you can get I2 Z2. So now we can get E2 minus I2 Z2, which gives E2. So in the direction I2, we have to draw I2 R2 from V2. Then you have to draw perpendicular to I2 R2, I2 Z2, sorry, X2. So by combining these two, I2 R2 plus I2 X2, which gives I2 Z2, E2 minus I2 Z2, which gives V2. Similarly, draw I2 dash opposite direction. I0 will be the no load current. Draw the parallelogram and find the resultant. I1, you have to draw E1. From E1, draw I1 R1 parallel to I1, I1 R1 perpendicular to that I1 X1. Joining this, you can get I1 Z1. So E1 plus I1 Z1, which gives V1. which gives the similarly more capacitive load. So I as the reference, E2 is the induced EMF, I2 will lead E2 as well as V2. I2 will lead, so I have to draw I2 dash. So from E2, so E2 minus I2 R2 minus I2 J into E2 E2 minus I2 R2. So I have to draw in the opposite direction I2 R2. Perpendicular to the top, this one will be, so from V2, sorry, from V2 you should draw. From V2 you have to draw direction I2 R2. So perpendicular to the top, this one will be I2 X2, I2 R2. Then joining this I2 Z2. So E2 minus I2 Z2, which gives E2. Similarly, you have to draw I0, draw the parallelogram, which gives I1. To draw E1, from E1, let's draw I1 R1, I1 R1, perpendicular I1 X1, joining this I1 Z1, joining E1 plus I1 Z1, which gives E1. Based on that, we have taken that will be equivalent circuit. Also, then comes under the OC test and AC test, test of the transformer, open circuit test and short circuit test. Open circuit test and short circuit test. So under this, we have to open the secondary winding and short the secondary winding. While you are opening the secondary winding, in the case of opening the secondary winding, whatever may be the reading that voltmeter gives for last. So because winding made of copper, so only the current flows through the primary winding. So due to that, the flux which will be produced links the secondary winding also. EMF is induced, the core takes more part, and because of secondary winding is opening, so none of the current flows in the secondary winding. So only the current flows in the primary winding. Due to that, it produces the flux links the secondary winding. More of the core part will be take place, so that the voltmeter reading gives that formulas. So and also we can identify the input voltage and input current I input. From that we can identify the power P is equal to P into I. So from that we can calculate the efficiency also. So by using the open circuit test and short circuit test. So in the case of short circuit test, what to do means we have to short the secondary winding. For that we have to connect the voltmeter and the ammeter and short the secondary winding. So we have to identify the short circuit current. So short circuit current with the help of ammeter, ISC, so VSC. So output power will be VSC into ISC, and also so we have to identify that will be if you are taking that will be watt meter. So in the case of meter and voltmeter, which gives that output power. So here we are identifying the core loss in the primary side, and we have to identify the copper loss in the secondary side also. That is, so here we are short circuiting the winding. So what happening? More current will flow in the secondary winding, so that we can get the loss in the winding. Comparatively, the flow loss will be lesser than the copper loss, so that we can identify the wattmeter reading which gives that copper loss. Use the copper loss. So in that secondary short circuit test, SC test. In the OC test, we are getting the core loss. In SC test, we are getting the copper loss. So total loss we can identify that will be core loss plus copper loss, 4 plus copper loss. So we know the input power P equal to V into I. So the output power we can identify input power minus losses. So the efficiency we can calculate output divided by input. So input minus losses divided by input, which gives the efficiency. So short circuit test also called as for inference test. So under the loaded condition, we can take the transformer under loaded condition. Simply we have to represent the transformer with it for winding and core. The two lines represents the core, and winding also the primary as plus secondary winding. Primary winding. So we are giving the supply to the primary winding. Across that we have to connect the voltmeter across the lines. Meter with the line is and wattmeter. Then the secondary winding also the same thing, voltmeter, this 1 meter and voltmeter. However, we are changing the load. We can measure the primary voltage, primary current, primary voltmeter reading, secondary voltage, secondary current, secondary voltmeter reading. From this board, we can calculate for every load. We can get voltage in the primary side and the secondary side we can get. By using that, we can identify that will be efficiency, output by input. The output power increase, secondary voltage into our wattmeter reading, secondary wattmeter reading, by primary wattmeter reading. For each load variations, we can identify the efficiency as well as we can identify the percentage voltage regulation, that is nothing but load regulation as well as that is upload regulation and download regulation. So download regulation. So upload regulation is nothing but V no voltage minus V load divided by V load, that is up regulation. In the case of download regulation, the download regulation will be nothing but V no load minus V load divided by V no load. If it is terms of percentage, you have to multiply by 100. So these are the things have been seen in the transformer. Based on that, we have seen the problems also. And drop in the secondary winding. So we can identify the drop in the secondary winding. So for that we can take I2 or not 2 cos phi 2 plus x naught 2 sin phi 2. So from the drop will be, we can identify. So secondary voltage can be calculated from the given minus drop is the secondary voltage.